Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
Hello, everybody. Welcome.
Hello. How are you all doing?
We are one day early.
Yes, yeah. There's always some changes to the schedule as needed, as we both have other things going on and projects and travel and stuff like that.
So you have to be on your toes. If you think we're going to be here on a Friday, all of a sudden, whoosh, it's Thursday.
No, actually, you don't really need to be on your toes. All you need to do is turn on the notifications if you're on YouTube or on LinkedIn. Follow us, and you won't have to guess, because usually at least a few days beforehand, we'll announce when the next episode's going to be.
That is the better.
That's the better
way to put it, and that's like the social media thing you're supposed to say. Like, tap that notification bell, like and subscribe, and comment for more content and what all the things that
and that'll also help you know when we're going to be coming on.
Exactly. All those things, you see those and you watch like videos or you watch, podcasts or all those things, and they always have the litany of things, right? The litany of
asks.
Yeah, exactly. Yeah. And there's always that click button, like tap that notification bell, ding, and there's some sound effects. Just me? That's fine. Yeah, just me.
No. It's good. It's also free. Like all the things that we ask you, the liking and the subscribing, they're all free. They don't cost you anything. They barely cost you time.
It's only 8 easy payments of $199.95. That's it. Do you remember that? Remember all those infomercials? It used to be like who fell for that? It was like only 712 easy payments of a nickel. It's like, can you just tell me how much it is?
I know. I think a lot of people use it. I think that the electrochemistry community, very smart. They don't fall for this kind of stuff.
That's right.
But other people, if they're not thinking about it, they don't do enough math.
Like this many payments of this much. It's $100. Okay, don't tell me 10 payments of $9.99 plus processing fee plus I'm bored fee plus it's $100, right? You want the thing, give me $100.
Yeah.
Can we just go back to common sense in marketing? I digress here. Well, welcome everybody. We are here to talk about electrochemistry, and Parthipan has a question about faradaic efficiency. So he's asked, why does the faradaic efficiency formula vary for each application? So as best I can guess, what you're referring to is that like sometimes you'll have a process where it's like, all right, the efficiency is measured by like the current I get at okay, I'll make up an example. I don't know if these numbers are real or not, but like, okay, I'm studying hydrogen evolution, right? And at 0 volts, maybe a little more negative than that, whatever, like at minus 200 millivolts versus NHE, I should have like 10 milliamps per centimeter squared, and I get 8 milliamps per centimeter. So like in some cases, the faradaic efficiency might be like 8 divided by 10, so it's 80%. Like it's a unitless number, but it's like the current divided by the max current I for whatever reason feel like I should get. Okay, and then in other cases, you might do like chronoamperometry or chronopotentiometry for a while, right? And you get current passing over a certain amount of time, and so effectively the integral of the current over time is the charge that's passed, and then you might do the faradaic efficiency by saying, here's the charge I got divided by the like ideal amount of charge I should have gotten. So I was supposed to get 100 coulombs and I got 50 coulombs, so it's 50% efficient. Or again, the last sort of option I think that's somewhat common is a voltage one, and one of the examples of that tends to be in energy devices. So like fuel cells or solar cells, for instance, are sometimes measured, I think, that way. So like a fuel cell, like a proton exchange membrane fuel cell, has an ideal voltage of 1.23 volts. That's the oxygen reduction reaction standard potential, right? And when you make a fuel cell, you often get like 1.1 volts. And so sometimes I think people will get a kind of efficiency by dividing 1.1 divided by 1.23, and it's like, oh well, that's like whatever, 85%, 90%, whatever it is, right? So why is it different, right? In some cases, I think the answer is that it's whatever metric is the most meaningful, and others it's whatever is more measurable. um, it does highlight, I guess, to the question asked here, which is a good one, which is like, well, how can we compare things when we're, calculating them based on different metrics? Like they're all efficiencies, they're all unitless percentages, for example, but some of them are like current efficiencies, and some of them are voltage efficiencies, some are charge efficiencies, right? So it definitely is, I don't know, relevant to bring up um, difficulties in comparison across different techniques when their efficiencies are measured differently. But just again, as a sort of an example here, it's like something like a solar cell, and I might be speaking slightly out of turn here because I'm not perfectly well versed with solar cells, but like solar cells are very like famously inefficient. They're very, very inefficient. I think that has to do with the amount of current you can get out of it compared to what like energy is found in like a like sunlight, basically, or something like that. So it's like how much, in that case it's like how much current can I deliver um compared to how much like current would be in an ideal like ray of sunlight if you just like converted it all to current or energy or
Mhm.
whatever. So it's something like that, and you get like 12% or something, and it's abysmal, right? But I mean, that's why solar arrays, like solar panels, it's a lot of them, is a lot of surface area. So even though it's low efficiency, you can still get appreciable amount of current to, you know, uh, to power your house or your whatever device. Okay. Now, in some cases, with like a fuel cell or another device, you're more interested in power, for instance, like deliverable power, and that's more highly dependent on the voltage. Um, the generally speaking, you're interested in how much current it can deliver, but if it doesn't have a high enough voltage, your power will be severely limited. Um, and so we're looking at like, well, how efficient is the volt? Like, is the voltage um, where it should be, so I can get more power out of it? So like its efficiency is more related to its application, right? Of deliverable power or something of that nature. So um, that's the best kind of somewhat general, if you will, answer that I can give for like why they're calculated differently. Again, some of it might just be the relevance or the convenience of the measurement. Um, the whether you're more interested, let's just say, in a deliverable current, a deliverable power, charge, voltage, whatever, and then some of it again just being what's more convenient to measure. Um, it's more convenient to just get a quick voltage measurement, see what it's supposed to be based on what thermodynamics tells you, and then that's an easy way to get an efficiency. And then in other cases, we really want to see how much current we can get out of it, and et cetera. So it's a good point though, and it kind of does bring up one of those just general things about electrochemistry, which is that it's just the worst. Because not only can we not figure out whether positive current or negative current is reduction or oxidation or what direction our plot should go, we don't even know what's efficient. We just don't. And the only thing we do know is that we, as electrochemists, are extremely inefficient. So, with that, I yield.
Yeah, no, I think yeah, I think that the question you have is also a very broad one as well, because like we need a little bit more like specifications, sort of say, with like, okay, well, what formulas are you talking about? But I think faradaic efficiency, just to kind of echo Neil's points and add some of my own, because you're just trying to look at how much, like, faradaic efficiency has always been about what we actually get versus what we should theoretically get. That's always in some ways what what the faradaic efficiency is talking about. I remember from like CO2 reduction related chemistry that, oh, you're trying to figure out a faradaic efficiency for like, well, how much CO2 reduced product did you get? And I think the methodology in some ways was always a little bit different. Some people were comparing CV curves when it came to efficiency. But really, it was always about, well, how many moles of a CO2 reduced product did you get? Convert those moles to the equivalent number of electrons of CO2. So if you formed something like methanol, it's a 6 electron transfer process. So depending on the equation, like depending on the reaction you're running, the number of electrons transferred will be different. That'll affect your faradaic efficiency. And then considering that number of coulombs of charge for the moles that you physically measured, what should you have gotten based on what your potentiostat measured? And faradaic efficiency is also tricky because sometimes it's the efficiency of one particular process that you're interested in. But it's often the case with some catalysts that you're not only producing like a CO2 reduced product, you might be reducing protons to hydrogen, and you don't want that. But it's not like the coulombs went into some kind of useless thing like a non-faradaic process. It just didn't go into the process that you were interested in. So that's another kind of thing about faradaic efficiency that I would add to that, is that it's unique specifically for actually with rotating ring disc electrodes. Oftentimes you're trying to do the oxygen reduction reaction process, and you're trying to look at the efficiency for reducing oxygen to water for electron transfer process. But the rotating ring disc electrode really shows you how good you are at figuring out how much peroxide you've generated. So you're generating like multiple different products. You have the collection efficiency of the ring disc geometry itself to contend with. So different formulas need to be used depending on the technique in that case, because there's layered theory, sort of say, within the theoretical collection efficiency, sort of say, that you can get. So I don't know if that helps. If you want more, if you want to ask us more questions or ask for more clarification, I think we can probably do that. That might be helpful. So so hopefully that was good.
And just so you're aware,
Mhm.
Shelley, Mintier Group,
Yes.
the duck. I'm making it front and center. It was. I'm glad you noticed it because it was cut off, right?
Slightly cut off.
Yeah, it definitely is getting. Yeah, there we go. That's a little better. It gets covered when the questions come up, so apologies, but he's there.
He's there.
He's there.
Yeah.
He's there for you. Geeky Nachos has asked a really good question: how to choose an appropriate method to calculate active surface area. So basically, like ECSA or electrochemically active surface area is. I'm guessing is your question. I can talk a little bit about this, and I just thought it might be helpful. I actually, once upon a time, was curious about this as well, where it came from, for instance, with the famous example. And I have the paper. I'll just show it to you because I think it's kind of helpful for the, I don't know, history of this. The most common method is for platinum. Okay. And we do this by using knowledge of the specific amount of coulombs per surface area on platinum that is associated with the hydrogen adsorption desorption process. So on platinum, at close to 0 volts, basically near the hydrogen evolution reaction, there's a process where hydrogen adsorbs or desorbs, depending on which potentials you're going through, onto platinum. So you get like platinum plus H gives you PTH. It's not worth writing it out. It's not that interesting a thing to equation to look at. But effectively, the method is to say, and I can show the method as well, but basically that process has an associated a specific charge of 210 microcoulombs per centimeter squared. And so let me just share this paper. I went digging one day, as one does, for where did this come from. And as best I can tell, this is, if not the original source for it, it's one of the original. So it's a publication from 1971 by Biegler, Rand, and Woods from Australia, apparently. So this is a paper, again, just trying to give a credit where it's due, right? Electroanalytical chemistry and limiting oxygen coverage on platinized platinum, relevance to determination of real platinum area by hydrogen adsorption. So these researchers, I don't know if they made the original measurement. I know there's some other references in here, but this is, again, one of the earlier mentions of this. But so this is the sentence in the paper that is kind of from which all of our electrochemistry, like platinum ECSA measurements, come from. Okay. The charge associated with a monolayer of hydrogen has been commonly taken as 210 microcoulombs per real centimeter squared. And so it's based on, because there's a 100 plane is primarily the one. You can see that what that actually comes from is that there are multiple different measurements that were taken. 208 for the 100 plane, 241 for the 111 plane. This is the better one, 111, generally speaking. But the reality is that polycrystalline platinum has a lot of different crystal facets involved, and it's mostly the 100 plane. And then these other ones for the 110 plane, which isn't as common, I think. And so there's some averaging that is done, I guess, and you end up with 210. So that's just become the accepted number. And the way that this was measured, quite simply, was that either these researchers or other ones got like pristine platinum samples and like ran experiments to adsorb platinum on it and measured how much charge. I mean, it's literally as simple as it sounds. Like they measured the charge with a potentiostat or with a multimeter, with, I don't know, something back in the, I guess, late 60s, early 70s. And measured these values experimentally, how much charge was associated with the adsorption and desorption of hydrogen on those different crystal facets. And so that is where that came from. Now, as a general rule here, how to choose appropriate method, I'll just share one other paper with you because it actually highlights an important point. Which one am I looking at? Is it this one? Sorry, I have two papers open. I'm trying to figure out which one I want to do. So another paper that just references that paper that I just showed you. So I want this one right here. So, for instance, this is another paper. Again, I'll give the accreditation here just to give references. So it's from Sharma, Giergiek, and Anderson from Denmark and Slovenia. Critical thinking on baseline corrections for electrochemical surface area determination of platinum and carbon through hydrogen absorption, desorption, regions of a CV and applied catalysis B from 2022. So it's recent. The point I was making is that they also provide, which I haven't found in a lot of places, although I'm sure there is other examples out there, but the surface charge densities of 210 and 407, so is another number that is not as commonly known, for the hydrogen adsorption and the copper under potential deposition on polycrystal. So this is another one that is probably a little less commonly used, I suppose, but for those folks who are studying copper under potential deposition on platinum, it has its own measured specific charge on platinum. So all I'm doing with sharing these numbers for you is to say, as an answer to your question, how do you choose an appropriate method to calculate the surface area? To a large extent, it depends on whether there is like tabulated or reported, known, accepted, whatever the words I'm trying to use here, values for this specific charge. And to my knowledge, there may be, but I don't know of a lot of other specific examples other than the two that I just showed you, hydrogen adsorption and maybe copper under potential deposition. I don't know a lot of specific reactions for which people have, reported a lot of those values. So like you're studying, nickel or copper oxidation of organics or something. Well, is there a specific charge associated with that so that you can run your own test and compare? I don't know. There may be, but I don't know a lot of examples of those, like those having their own numbers as well. So that's the tricky thing. So how do you choose an appropriate method? Well, if you have a platinum electrode, it's quite easy. Get some sulfuric acid, get up your platinum electrode, know the um, uh, um, the
Well, do the CVs
yeah,
of it in sulfuric acid, get that region.
Yeah, I was just thinking, because I'm gonna show I'll show it. I'll draw it really quickly here as I. So the process for that again is run a CV right around 0 volts. You'll get something like this will be your CV for platinum and something like that.
Yeah.
And basically what you're doing is you're going to take away the background current, which is in this thin region right here. And either I'll color it blue down here, this area, or this area here basically corresponds to, this is the platinum hydrogen desorption, and this is the platinum hydrogen adsorption. Adds. There you go. Now you have to do the current versus time to get charge, but basically integrate. I'm actually drawing this incorrectly. This would integrating in the CV will give you watts. It's the wrong unit. Anyway, the point is, and I'm sort of assuming that this is somewhat of common knowledge for folks who are doing this kind of thing, but what you're doing is effectively getting the charge associated with this. And so that 210 microcoulombs per centimeter squared. And so if you get, 1 microcoulomb, well, then 1 microcoulomb divided by 210 microcoulombs per centimeter squared means you have 1 centimeter squared ECSA. So whatever you get for your coulombs allows you to calculate your ECSA this way. So it'd be the same with a the problem is that for any particular electrocatalyst or system, what's the appropriate method, right? Mostly you have to use physical characterization methods if you don't have these kinds of things, like specific charge associated with a process that you can do with a CV and do stuff like that. Hopefully the audio is working. I know sometimes when we've shared screen and come back, thank you, Chris. Yeah, the audio does weird things. I hope it is okay. So anyway, all my point is that in some cases, the active area is simply taken to be the geometric area, or people do like BET analysis to figure out the specific surface area per mass. You have a milligram, it's this many square meters per gram, and so I have this many square meters or square centimeters of area, and you assume that's the electrochemically active area because there's a difference between geometric area and electrochemically. So it's unclear, is sort of my point, for reactions that are not that specific one, like platinum, copper under deposition, or hydrogen absorption, and it definitely becomes murky. I will be honest. I'm not terribly aware of electrochemical methods other than those ones that I just showed you for calculating ECSA.
There's another technique you can use as well. That's a little bit more. It's a little bit more general, but it requires perhaps a little bit more work. But if you use the Randall-Sebzich equation from cyclic voltammetry, so this is the full Randall-Sebzich equation. This is the Randall-Sebzich equation for room temperature. But one thing that some people do if they really need to figure out what the electrochemically active surface area is if they have a redox active molecule that they know about and that they understand, what they can do is they can actually independently. So again, you have your voltage versus current, you have your duct, and let's say you're doing an oxidation reaction. So this would just be like red is becoming the oxidized species plus an electron. One thing that you can do is you can do some work to try to basically this peak current, which is this value here, right here, that's equal to all this stuff, the number of electrons transferred, the area, which is what we're solving for, concentration, scan rate, and then the diffusion coefficient. You can either do separate experiments to determine what the diffusion coefficient is for this specific process independently. There are many ways to determine the diffusion coefficient. You can use a rotating disk electrode. You can do impedance spectroscopy. You can look in the literature to try to find some values. But once you find a diffusion coefficient for this specific electrochemical system, so this will change ever so slightly depending on the electrolyte that you're in. You can then back calculate based on the peak current what the area is, and then you can even vary the scan rate so that as you get either lower scan rates, and then of course it's also going back this way. I can't draw very well, but
That's an interesting CV.
I can't draw very well at all. And of course there's other stuff. But as this changes, you can do like a linear regression, and you can so you have like square root of scan rate, and then you have peak current, and then this is the known, this is the unknown, and then you plot this to y equals mx plus b, and that will probably give you a more accurate a more accurate calculation of the area if you're not working with platinum and you're not using hydrogen, for example. So that's another way, and it's not like 100% accurate, but because if you have a really big bulky molecule, well, its diffusion coefficient, it might not be able to access all of the area, sort of say. That might be electrochemically active. The nice thing about platinum and hydrogen is that hydrogen is it's the smallest atom, so it can get to every single facet or spot on your platinum, your polycrystalline platinum. So that's kind of the advantage of it. And yeah, and so that's another way if you're confined, if you're working in non-aqueous systems, stuff like that. That's another thing that you can do, but it's a tricky subject. A lot of people can have issues with it. And similar to what Neil said, you would look at you could use that to do to figure out you're relating the peak current to the area, but you could also do some calculations with the area under the curve for current versus time. So you could do some stuff like that too.
Chris says your duck is drunk.
I know. It is it's very drunk. He had
a rough week in the lab.
Very rough.
All his data was bad. His potentiostat stopped working. Reference electrode problems. It's been a tough week.
Yeah.
Dune Girl has said how to find CV for lithium-ion batteries in COMSOL. And can you show me a demo? Unfortunately, I can't. I don't have COMSOL.
Yeah.
So I'm guessing you're doing, simulations or numerical, studies of batteries and everything. And I don't have COMSOL, unfortunately. I can talk about batteries and CVs and things like that. But if you're trying to, make a CV or simulate the data, I suppose, I unfortunately I can't help you in that regard. We do have simulation software, like our company has simulation software that can simulate CVs, given knowledge of like kinetic parameters and E0 and all the different things. So you could, in theory, simulate the CV of a battery if you know all of the parameters associated with it. But I don't have COMSOL. I unfortunately I can't show you that. I'm sorry.
Sorry.
but feel free, Dune Girl, ask if you need if you want to follow up general questions, not specifically related to COMSOL. I'm happy to talk about them outside of that software. I do know COMSOL. I've used it. I don't have it. I don't own a license of it now, so I can't do anything for you. Tamogna has asked, "Hi, I saw your video regarding how a potentiostat works, and that was really illuminating." Well, thank you. I just want to know if I take two potentiostats and connect two working electrodes to connect two working electrodes from two different potentiostats and attach the same reference and counter electrode to two different potentiostats, could that become a bipotentiostat? No, that won't work.
You need a usually like Gamry, for example, has a configuration where you can do something like that, but they have a special
you have to
cable.
ground something, has to be ground properly or whatever. Yeah, it won't work just that simply. So the circuitry essentially of a bipotentiostat is a little more complicated than that. It works basically the way that you're imagining using two potentiostats. It basically works that way, right? It's like two working electrodes are coupled to a single counter and a single reference electrode. But if you just put two distinct potentiostats together and hook them up that way, it won't. I don't know exactly what will happen, but it won't work the way you think. I think effectively is that both potentiostats will be fighting over the same reference, same counters. If again, I might not know perfectly well. I'm not an electrical engineer. Alex made the video on the how potentiostat works, and I did a webinar on it. Basically, we've stolen and recycled the same content, you and I. And by that I mean I stole what you made. So anyway, but the point being that neither of us are electrical engineers, and so specifically my knowledge of precisely how the circuitry and the feedback loop works with a bipotentiostat as it gets somewhat more complicated is incomplete.
This might require a consultation with John, our electrical engineer in the future, and ask us, "Hey, John, you taught us how a regular potentiostat works. Can you show us how a bipotentiostat works?" And I know, like in our circuit, one of the keys is that there's basically another operational amplifier in that controls that second working electrode, but how it's tied together.
The tricky thing, of course, is that you think about like the counter electrode gets the equal and opposite, not exactly voltage because you have a reference electrode, but just consider that it gets the equal and opposite current from the working electrode in a potentiostat, right? So you can imagine if like 1 milliamp is going to the working electrode, the counter gets minus a milliamp, something like that. Right.
Yeah, the current is equalized.
Right. So all my point is that if you imagine, for example, you can have a situation with a bipotentiostat where working electrode 1 has 1 milliamp and working electrode 2 has minus 2 milliamps. Like I'm just making up numbers here. Like that can happen. And so the counter electrode would have minus 1 and plus 2. So it's like two potentiostats connected in the way you have would, I think effectively like what they're fighting. Like one of them is trying to push 2 milliamps into the counter to balance, and the other one's trying to draw a milliamp out. And it's like they're fighting because, one of the other things, again, from our video on this is that effectively the potentiostat controls the counter electrode to get the working electrode where you want it. And so it's like both distinct potentiostats can't both control the counter electrode voltage at the same time. The bipotentiostat has a method, like there's some grounding thing or something has to be ground. I think like when Metronome and Gamry, as you said, they have a way to do that, but it's not as simple as you describe. You have to get an extra cable or you have to ground a thing, something. One of the counter lines has to be connected to ground or something like that. Again, I'm sort of speaking out of turn because my company makes integrated bipotentiostats. So I actually don't know 100% how the other companies
how they integrate two single channels into a bipot, which is technically it's weird that because we've commonly thrown around the language of quote true bipot, where like the circuit is designed as a bipotentiostat. It's not like we just ganged up two single channel potentiostats and then called it a bipot.
It's more efficient, if you will.
Yeah. It also has way less cable mess, if you will. in that configuration.
There are benefits to why we do it the way we do it.
Yeah.
And actually, Pine was the company that made the very first commercial bipotentiostat.
Yeah, I think so.
Was it the CBP? Or was it?
It was one of well, they used to call it like the RRDE like 5 or something like that.
Ones,
but it was an analog bipotentiostat
Yeah.
that could control two
And
two
it wasn't
working
two
electrodes.
potentiostats with some kind of a ganging cable operation.
Yeah.
So our company is the one that made the first commercial option there.
But it's a good question. I think that's something that
Yeah.
like I would like to know at some point.
Yeah, it would be good to know exactly how the circuitry works there.
Yeah, how the
It is
bipotentiostat
fascinating.
works.
I feel like if we try to learn that, you and I will be very confused for another year until we.
Oh yeah,
start understanding.
yes, yeah,
It will
yeah.
take
that's
time.
True.
It will take a lot of time to figure that out. But it
Mm-hmm.
is an interesting concept because the long and short is that I mean, I can speak for myself, but you're
Mm-hmm.
probably the same. It's like I didn't know a lot about the specifics of the operation of these kinds of devices that I used in graduate school and as a postdoc. I didn't really understand them as well as I do now until I got now. And we had, I've expanded how much I know about these things as part of making these videos and these webinars and stuff. So it's very fun to fill in those gaps, you know what I mean? Cause I applaud anybody who's in graduate school learning how a potentiostat works. Like it almost never occurred to me that I would be able to like understand that when I was in graduate school. So I like to see people being inquisitive about those kinds of topics. It's cool.
Oh yeah, yeah. And you can control so much more about a potentiostat now than you used to. And even the history, like our boss used to have like there used to be these big analog boxes. He'd be like adjusting like dials and knobs, and I'm like, what do these dials and knobs do? And it's like, well, you can control that now in the software, but they always seem like it seemed like it was important back in the day to control the dials and knobs, and everything was like automatic. Now,
people used to have to get up off of their couch and walk to the television to change the channel too.
Oh yeah,
that was
they didn't have remotes.
Yeah, and you would click the thing. I remember my grandparents had a TV with the big dial, and you click it, and it was like, but it like skipped certain channels. Like it just knew there's no channel 1 or 5 or like 15 for some reason, and it would just. It'd be like 2, 3, 4, 7, 12, 36. It's like, what? Who programmed these numbers? This is not how numbers work. Why? What if I want to watch channel 11? There's nothing on channel 11, really? I don't know.
Yeah. And back in the day, we used to get DVDs that we'd have to like put into a DVD player.
DVD.
And we used to, and you couldn't just get something instantaneously on the internet to watch like a brand new movie automatically from your couch without even moving. You had to rewind VHS tapes. Anyway, I'm sure
we could go down
this rabbit hole.
This is just like, how old are you? Do you remember?
Do you remember?
I remember life before phones and social media. Can you believe that?
Oh,
being in school without a phone. I mean, imagine that.
Yeah.
That life existed. You and I are in the generation, like the last generation that remembers what that was like. Effectively.
Probably.
Millennial, like we're the millennial-ish generation or whatever. Or Gen X, there's different names for like whatever you categorize it, but people who are like high 30s, low 40s age or whatever are the last group of people who, when they were kids, there was a time where there were no, phones, no.
All you could do is text. And
even then,
we were at barely the edge. I think I went to college before texting was actually like a very important thing.
And it wasn't when texting came out. It was like just when I was in college, like starting college, or end of college, even or whatever. Like towards the end of it. And I remember being like, "This is dumb. No one's ever going to do this."
Yeah, because like you had to go through the numbers. Yeah, like there wasn't a little keyboard on your screen
to spell a word. Took 45 minutes.
Yeah,
and then they got T9. Remember T9?
No.
It was the first sort of predictive text, because like otherwise you had to get a C, you had to type 222.
Yeah,
that would A B C. All right, and then it's like H is like G, like whatever the number of times you press it. So it's like if you had a word that had all of the third letter of each number, you had to press the numbers 15,000 times. So there was a predictive thing. It was called T9, where it was like you would press like 25183 whatever, and it was like it's one of those 3 letters of each of those, but there's prediction where it's like if you're putting the word love and it's like whatever the 4
because there's not that many LOV and like
LOV like F, you
F,
know. So
T.
so
Yeah.
anyway, and it wasn't right all the time. There were some like common words that could be done. Anyway, I'm so dating myself here, but I used to like that.
Yeah.
I used to like T9.
Chris remembers that.
Carrying a
Chris
pager.
is-
I never
yeah.
had a pager. I think I wasn't important enough. You know, like if you were
Oh,
if you
yeah.
were like a doctor or a
business
per-
important business person
yeah,
had a
you would
pager.
have a pager, and it would be that little device that was like, call this number, you know, and then you'd have your phone. And for some reason, pagers and phones were two different devices. You couldn't just have your
Yeah,
phone tell you call the number, you know.
Which I never understood because we had mobile phones
I know.
and pagers at the
Or
same
like,
time.
or it was like you got your pager, you had to call on the car phone. Remember car phones? I remember being in a car in like the early 90s, 1990s,
Mhm.
and it was like I wasn't, you know, particularly wealthy. Like my family wasn't rich, and it was like I'd be in a car with like one of my friends whose family had some more money, and there was a phone in the middle. You know what I mean? Like in the front seat, like where the console is, where like, you know, sometimes there's like compartment, you keep tissues in it, you keep, you know, whatever, and it's like that was just a phone, like it was the size of like, you know, it was the size of like
two of these mugs.
yeah, I don't know, I'm trying to think of a funny example, but it was just enormous, and it was like, and it had the curly,
Oh yeah, it had an antenna.
the curly antenna, yeah, exactly, and it was a car phone. Like this was a thing. It was like, oh my, you could talk on the telephone in the car.
Yeah.
Oh my gosh. And it's like, I remember being like, oh my gosh, how rich do you have to be to have a car phone? And now we all have these.
Yeah.
I miss the simpler times.
Uh,
I do.
I think about the simpler times. I also think like, there's pros and cons.
Yeah.
But I mean, like,
life is more convenient now in a lot of ways.
it is. I also think like medical technology has always been like, oh yeah, I'd rather be alive today because nowadays they have to like cut you open to do something. It's like, nope, they can just put a little tiny thing here and make an adjustment, and that was your surgery.
Yeah.
And I'm like, wow, that's incredible.
There's almost no time in history where you'd want to be alive if you had a medical problem.
Yeah.
Like it's always now or later. Or later. Yeah.
Yeah.
AMPS bricks. I don't know what AMPS bricks are.
Amps bricks.
Amps bricks? What's an amps brick?
I don't know.
What that is.
We do have.
Sorry,
there is one question that we haven't gotten to.
Yeah, Shandan has a question here. You should probably dig into this.
Sure. So Shandong is asking how reference electrodes are made so that their potential remains constant. This is a very good question.
They are given a stern talking to, and they say, you will stay constant or else.
Or else.
And they follow the rules because you have a strong discipline.
Because you know, if you don't stay constant, I'm gonna refresh you.
Yeah.
Okay. You're gonna get a stern refreshing from me.
I'm gonna send you to your room and you'll think about what you've done. It's such a bad dad joke. I couldn't help it.
So there are a couple properties to reference electrodes that are very important. And ultimately, I'm just going to bring this up, but ultimately the important thing about reference electrodes and what their potential is that the potential is governed by a certain equation that is enjoyable. It goes by the Nernst equation. And shocker. And what the Nernst equation basically states is the potential of your system, really, if we think about the metal or your system, is equal to the standard potential of a redox reaction minus RT over NF times the natural log of the activity of the product divided by the activity of the reactants. So products divided by reactants. So this is a situation in electrochemistry where, say, we just have a metal, because most of the time a reference electrode is just some kind of metal wire. It's in a tube, and I will try my best to draw straight lines in this. So we have a metal in a glass tube. All right. It's filled with solution. There's some kind of frit at the end. And sometimes there's something else here. Like instead, this may be a silver wire. And then we have silver chloride here, AgCl. And the potential of the metal, which is the silver, that our potentiostat reads, so this goes to our P-stat, is governed by this equation, right? So the potential that we want to be constant is based on this equation, right? How does this become constant? So it's constant because, well, we have a constant here, but if we keep the concentrations of these guys the same, so that the activities or concentrations, as long as we keep them the same, they will not, this will hold, this potential will move. Or sorry, if we keep these the same, this will not move. This will stay the same. So this inside this solution is usually something like saturated but 4 molar potassium chloride, right? It's and the reaction in the case of KCl is something like this. And I always kind of get this somewhat backwards. Let's see. So plus an electron is equal to Cl minus plus silver metal. And this is a solid. And so if we kind of remember our rules, sort of say, of chemical equilibrium, because this is a solid and this is a solid, it falls out of the equilibrium equation. This is the activity, if you will, of chloride ion. So the chloride ion concentration is the only thing that governs this. If I have 4 molar potassium chloride in solution, well, for this to drop, right, for the potential to change because I have a natural log, there needs to be a factor. What generally happens mathematically is that it takes a factor of 10x the concentration, creates a 59 millivolt difference in the potential. 10x. That means my 4 molar potassium chloride has to go to 0.4 molar for me to observe this kind of difference in the potential. That's pretty big. That's a substantial change in concentration for me to observe only basically 60 millivolts of change in my reference electrode potential. So this ultimately is the reason why reference electrodes can maintain. So it's the Nernst equation. That's why it can maintain a constant potential. But there are a few other factors, not a whole lot, but you may ask the question, well, what if I had another redox species in here? Like, what if there was a competing, like, I'm usually doing this in an electrochemical test solution. This is a porous frit. Stuff can get in here, right? So why does this reaction govern the potential of my wire when another species can go in? And the key here is that we didn't draw this out, but there's a rate constant associated with this, right? There's like a K1 and then there's like a K minus 1. The rate constant associated with this was whichever redox reaction has the faster electron transfer kinetics, that is the thing that governs the potential. So that's another thing. And then we usually say kind of the last thing is it's kind of it's a weird point, sort of say, but that is we want our reference electrode to be what we call ideal non-polarizable. So if I have potential on one axis and current on the other axis, we want, and this is called a ideal non-polarizable electrode. And we want something that looks kind of like this. It looks like a straight line. And usually it may deviate a little bit at very, very extreme currents. But the idea is that no matter what within this range of current, which is pretty big, like a huge current range, the potential remains the same. So some people may actually do these IV curves, and they may actually see like, hey, this metal that I'm using for my reference electrode, that does not change while I drive quite a bit of current through the system. So ideal non-polarizable electrodes are what you want. That gives you the feature. And conversely, your working electrode should be the opposite. It should be an ideal polarizable electrode. You want to be able to pass lots of current or have a big potential window where not a lot of current passes. This is what you want your working electrode to be. You want them in some ways to be opposite. So ideal for reference electrodes, ideal non-polarizable electrode, fast electron transfer kinetics, which is this, and the potential is governed by the Nernst equation. Those are the three things that are required for having a reference electrode, and why a reference electrode maintains its potential. So with that knowledge, you could actually make your own reference electrode if you follow those three things.
Or we could find a way to get rid of them.
Which I know that's your goal. Your goal is to
you will know that I've achieved my goal when you never see me again on this live stream, because I will have discovered a way to get rid of reference electrodes permanently. We don't need them somehow. There's a scientific answer to this. It's like light speed travel. It's my holy grail. Someday I'm going to be like, what if we just connect the potentiostat this way, and then you don't need a reference electrode.
You don't need a reference
and then all of your problems will disappear because they all come from the reference electrode, and I will retire a super duper billionaire because everyone will give me money for figuring that out. This is my career goal. It's important to have goals.
It is important to have goals.
And until then, I have to keep working and doing this live stream. I mean, I love
Chris, that's a good idea. Need to put the Nernst equation on a t-shirt.
I know.
Come up with some funny pun.
Yeah. Just be like, it all comes back to the Nernst equation.
All comes back to the Nernst equation.
Find some branding opportunity here. That would be pretty funny.
Oh, that would be
Until
funny.
then, we will press on.
Yes.
And Delvin George has said, can you suggest me a systematic way of testing an OER electrocatalyst? I mean, yeah, I can kind of, I guess, step through maybe
how to test
a process. So let's first define the oxygen evolution reaction. Mm-hmm. Why don't we? So the oxygen evolution reaction is the opposite of the oxygen reduction reaction. I'm going to draw it in acid just because it's the easiest one to remember. It's different. The reaction is different depending on whether you're in acid or base, but effectively, you get oxygen plus 4 electrons. I'm writing it backwards because I'm used to the OR, plus 4 protons, and it's 2 waters, I guess. 2 H2O. That balances. Yeah. Right. Okay. 2 H2O. So this is the oxygen evolution reaction, and it has an E0 of 1.23 volts. Excuse me. Now this is written as an oxidation, hence the oxygen evolution reduction is oxygen evolution reaction. Is an oxidation reaction, which means that at potentials above 1.23, it will take place in theory versus NHE. Okay. Excuse me. So, like a systematic way of testing your electrode. Well, the first obvious piece of information to think about is that, okay, well, I want to test my catalyst for the oxygen evolution reaction. I know for one, I'm going to have to get it into an electrode form, and I'm going to have to apply potentials greater than 1.23 volts versus NHE so that this reaction proceeds in the oxidation pathway, which is what I've drawn up here, so that I start basically oxidizing water into protons, electrons, and oxygen. Okay. So, I can speak sort of with, I don't know what you say, bias based on my company and what we make. But one of the more common ways of doing this is getting a rotating disc electrode. And so that is like a Teflon shroud with a disc, usually of glassy carbon. Okay. And so you'll have something like this. You have your glassy carbon disc. You get your catalyst in a powder form, make an ink of it, and basically deposit your catalyst onto the glassy carbon. And so I now have my electrode here and my material. This is my, my catalyst, my material I'm testing for OER. And then you're going to put this into a cell. So you're going to put the electrode into a glass cell, with counter electrode and reference electrode. And you're going to fill it with water, and you're going to do a CV. And when you do that, you're basically going to go greater than 1.23 volts. And so when you do that, hopefully you'll get some current. And so as you scan positively, you'll get an increase in current. Maybe it'll make a peak. Maybe it'll flatten out. Maybe you get some pattern basically. So this is one part of the testing is, and you'll have to forgive me for not knowing 100% of the metrics. In some cases, you're going to look for like, what is the current density at a particular potential? So you're going to do that. Some cases you're going to see, well, when does this start to go up? Like, do I have to go all the way out here for the current to start going up, or does it start going up here? So this is called the overpotential, essentially. So it's like it should happen at 1.23, but actually I don't get the increase until 1.6. So that's bad. Like, oh, this is a bad catalyst. Maybe it happens right at 1.25 here. So that's good. It happens right here. Maybe it doesn't. So you're looking for, when does the current tick up? How much current goes up? How much is it going up? Things like that. And then the last part of this sort of just very general, I don't know, talking through OER testing would be, you can measure the amount of oxygen that's made, for instance. So maybe in some cases you'll have a cell and you'll add to this cell, a gas tube where you'll seal everything else off and get a gas, outlet. And so you're going to measure the amount of oxygen that is coming from this. You purge it first, so it's all inert gas like argon or nitrogen, and you're going to measure the gas. Maybe you send this to a mass spectrometer or a gas chromatograph, or you have an oxygen sensor of some kind. Maybe you have a dissolved oxygen meter. So there's ways to measure oxygen. There's a lot of, maybe different methods for measuring oxygen, but you might be holding the potential here and then just generating oxygen and then measuring it empirically through some other method. So you might be doing something like that. There's probably a variety of ways in which people are doing that kind of quantification or studying it, I suppose. So that's somewhat of a quick, I guess, overview of like setting up an OER, set of OER tests, I guess. Delvin, if you want to follow up, even any specific questions about anything I just said. Again, I'm trying to kind of be quick and just give you a framework for how these kinds of tests might work. There's a lot of added things, for example, in the preparation of that catalyst that I skipped over just for the interest of time. Certainly there's probably a lot more in the analysis of the electrochemical data as well that I've glossed over here just to give a quick answer. But I don't know, that's about as succinct, I think, of stepping through, testing the electrocatalysis of an OER for a material, for how well it performs OER.
Very good. So, Chandra, unless there are any other earlier questions, it looks like Chandan is asking, does the reversible hydrogen electrode exist physically? And specifically, if then, what is the electrolyte used there? I think you can use any strong acid. So reversible hydrogen electrodes do exist, and they're kind of defined as it's like a pH sensitive reference electrode. So if you have a system at a specific pH, you can add the reversible hydrogen electrode and then in some ways adjust it so it's at the same pH as your system. And you can easily calculate what the potential of the reversible hydrogen electrode is by just, it's just a simple equation where I think you take like 0 and then it's like adding 59 millivolts per pH unit. I think I'd have to just look up the general equation, but it's not hard to, let's see. The potential is equal to 0 minus 0.59 times the pH, and that's how you figure out what the potential is. So of course the question is, well, this is an equilibrium. This is an equilibrium associated with H plus, 2H plus, and hydrogen. Where does the H plus come from? You need some, you need to add acid, and you can actually add any acid you want. I would actually pick a strong acid. Not, you don't want any weak acids. Something that just completely dissociates, to keep the concentration constant. So it's only based on what you add. But you can add hydrochloric acid, to get the pH to what you want. And I was looking at some, just there's a quick publication. I just did a simple construction of a novel reversible hydrogen electrode, and they just use hydrochloric acid to make the uh, reversible hydrogen electrode. So it looks like that's what you can use to make it. You still need platinum or platinized platinum to do so, but I think that is what you can use when using um, a reversible hydrogen electrode, or if you want to make one yourself. Hopefully that answers your question, but yeah, if so, we can continue. Continue to ask us questions if you need more clarification, or if something doesn't make any sense.
Nothing makes any sense.
Oh, that's also true.
That's not helpful at all.
It's acceptance. It's moving in the right direction to
Exactly.
accepting that we don't really know anything.
That's true.
And the closer we get to that, you can attain nirvana. You can be at peace.
That's so deep.
It's so deep.
That's so deep. We could just be at peace if we accept that we know nothing.
If we accept that we know nothing, the more that we know.
Well, I guess I'll continue being at chaos.
At chaos.
And pretending I know things. Like this. How is OCP different from corrosion potential?
That's a good question.
So it is not necessarily the case that the corrosion potential is the potential at zero current. Open circuit potential is the current, is the potential where net zero current is flowing. The corrosion potential is usually found by finding this meeting point between the two Tafel slopes effectively, right? And then, I think that what you're saying, I'm trying to think if there's probably a better like technical or theory-based answer, but what I can say is, for example, if the corrosion potential were always the same as the open circuit potential, then I core would be zero always, right? Like when you, for example, find the corrosion potential experimentally, you make the kind of Tafel plot commonly looks something like this. You'll have voltage here and log of current here, right? And then you'll have like two different curves here. So this is the cathodic one. You'll take the slope, and then the anodic one, you'll take the slope. And where I'm drawing these pretty badly, but just so you get the idea, where these meet, that right there is E core or V core, whatever the way you want to say it, right? And so the corresponding I here is I core. So it's, log of I core. So you basically do the mathematical transformation. But the point of this is that I'm saying is that you get this corrosion characteristics here, the potential and the corrosion potential and the corrosion current. Well, if this was the same as OCP, I core would be zero always, right? And that's not always the case. Like in some sense, practically, that isn't really what we observe. It's not always. And you can even see that log of zero is like infinity or minus infinity, whatever. That would correspond to like exactly this point over here. This is probably open circuit potential, and where these intersect is not always the same. As far as why, like physically or that probably is another question. Like what, like, I'm trying to think if there's a better way to, like,
Well, one thing about corrosion experiments is, or at least my limited understanding of it is like Tafel analysis is based on like A plus an electron goes to B, and B is equal to A plus an electron, a reversible reaction. But it's often the case in corrosion that what happens on the anodic side and what happens on the cathodic side are two different things. Like when you have a oxidizing potential and when you have a reducing potential, two different electrochemical reactions are occurring. It's not like the same reversible electrochemical reaction. So that's in some
that's why there's
ways
different Tafel constants for the anodic and the cathodic processes.
Yeah. So that may be a reason why, because OCP for a non-corrosion related process, it's like, well, there is no current flowing, and when you have, if you were to do the equivalent with a reversible redox reaction and do the Tafel analysis of it, you get an exchange current density, but where that potential meets the E0 is kind of when no current flows at equilibrium. So that would be the equivalent, because those two things, like the oxidation and reduction reactions, are equal and opposite. But I don't know if that's the case in corrosion experiments. That's kind of my initial thought.
I'm kind of trying to find if there's like even our this is one of these things that I feel like like semantics, almost like just on a definitional basis. I don't know that I've seen a lot of explanation about like E core and I core. It's like E core is the free corrosion potential. Like, what is that? Is that, like you said, it's like there's an anodic and a cathodic process. Is it like the thermodynamic potential between those two processes? Like, the balance, like E0 effectively between those two, or something of that nature.
Well, you can have, because I guess everything's in its own like reaction soup, sort of say.
Right.
And so when you bias the potential one direction, you're getting one type of reaction, and then when you bias it the other way, you're getting like a totally different reaction.
Right.
And like that's not it's the pure, like from Butler-Volmer to Tafel, those are all assumed to be like these single electron transfer reversible processes. But in corrosion, it's different. It's still the same, like it can be extrapolated, but yeah, I don't know enough about the physical meaning, like when you have, like what happens when you have a Tafel slope anodic that's very different than the Tafel slope cathodic.
I mean, you already said it though. I mean, effectively the reactions are different.
Yeah.
It's not necessarily one process where the oxidation is, the same reaction going this way, and then the reduction is just going the opposite direction. There are different, I think there's different processes that are occurring, something like that.
Yeah.
And I guess to me, it just feels like the E0 is like, because like you said, like if it's like O plus Ne goes to R, it's just one reaction. It has an E0 easy, right? But it's like corrosion's a little more complex than that, I guess, right? And you often, that's why it's complicated. Like you don't often see people really write out, well, here's the oxidation reaction. They just study the Tafel plot, for each way.
Yeah.
But they don't usually, maybe there are papers where they do, but like in a lot of cases, I feel like it's like, well, here's the anodic and here's the cathodic Tafel slopes or constants or whatever. But like, what is the chemistry? It's like, I mean, sometimes maybe the oxidation's a little easier. It's like, iron plus,
plus
plus
2
electron
plus goes to iron 3 plus, and there's oxygen that's involved in that process.
Exactly. Right. So iron gets oxidized. Okay. But like, what's the reduction? It's not necessarily making metallic iron, it might be something else. There's like a passivation film, or there's other stuff
Yeah.
like that's happening. And so
Mhm.
my understanding again is just that the E core is like you put a whole bunch of stuff, and even Chris says, like, you spend time in a boat in salt water, you get a lot of different reactions. It's like, yeah, there's a
Yes.
lot of, in a soup of stuff, which a
Yeah.
lot of times,
It's the
corrosion is
in the
in a
system.
brine.
Yeah.
There's, sometimes it's just plain salt. Sometimes there's other stuff. Sometimes there's gases. Sometimes
Yeah.
you have CO2.
Yep. Yeah.
So the potential is just the thermodynamic combination of all the stuff happening or whatever, right?
Yeah,
So
actually, that's a very good point.
so it's like
Yeah.
E core is sort of like the thermodynamics of all the stuff,
Yeah, like if you like, we often calculate a cell potential, right? It's
Mhm.
just like, oh, I'm actually doing open circuit potential of a thing, and then there's all these reactions that are in it, and we do the addition and subtraction of all these things, and we get some number, and that number is ultimately what like we kind of measure.
Yeah.
Ideally, when we do the open circuit potential.
Yeah.
Plate zinc on.
And so at OCP, it doesn't necessarily mean there's no corrosion happening, right?
Correct.
Because it means the net current is 0, but that means there's some flowing in all. You could have 1,000,000 amps flowing in one direction and 1,000,000 amps flowing in the other direction, and the net current is 0, but there's a lot of stuff happening.
Yeah.
So, yeah, that those are not exactly equivalent things.
There's also irreversibility
Yeah.
of some of these things. Like a lot of the equations are assumed to be like reversible, but a lot of corrosion, like formation of rust, I don't know. It seems pretty irreversible to me.
That's pretty irreversible. That doesn't go backwards. You don't look, if you could get rid of rust by just applying a negative potential to a whole stick of metal, and
It'd
it's
be
like,
on
whoop,
every ship.
every ship would have a battery with
Yeah.
a negative potential. Now, I will say this. I do think I have heard like some point in time through the grapevine that I do think that is like a technology that exists. I have to remember where I saw it, but it's like, I think there have been like R&D projects where they try to keep a negative potential applied at the it's like the surface of, maybe it's like a ship's hull or something. If you keep a negative potential applied, in theory, it would discourage corrosion.
Yeah.
Now, there's a lot there. Like, if the size of the metal is huge, it's going to take a lot of energy to apply a negative potential forever. That would just use up a battery in like an instant. So like, it's not maybe, like, and if, okay, whatever. So it's like, how much energy does it require to do that? Is that worth the energy that it would just take to replace the thing when it rusts anyway? Like there's a cost benefit analysis here or whatever. But I have heard of something like this once upon a time. I can't remember the specific source, but it was like maybe in some test cases, someone found that if you keep a negative like electric field around a metal in solution, it will gas lines are protected by a DC bias current. So this kind of thing.
Okay.
Of course it doesn't replay it out. So Chris is, there must be some cases where that can be done, but it's a cost, it costs energy to do that. So anyway, hopefully kind of talked through that again. I know some of that might be a little bit talking in circles. Himanshu, I know some of that is, I don't know. It's hard to give a direct answer. There's a lot there, right? We kind of talked through a lot of these different processes.
We need to learn and think a little bit more about that. That's a good question.
Yeah.
Need to learn about bipotentiostats and OCP versus corrosion potential.
Yeah. Well, you just learned about potential. So thought about potential for the last year. Now you can think about open circuit potential.
Yes. Well, yes. Yeah. I understand.
Potential.
Well, I understand open circuit potential. It's corrosion potential. I'd have to like look it up.
I think it's a lot like the exchange current density, which is why you can't stand it, because it's like,
it's a measure of how facile, how easy is electron transfer.
It's just weird to think about, like, this is it's like for me anyway, I think this way, where it's like, there's a specific system. I have like a catalyst, it's material, and it's in a particular electrolyte, right?
Yeah.
There are properties associated with that system. Like, I can accept that it has a certain set of properties, like it's good or bad at this, it's fast, it's slow, it has a certain density, it has a certain area. Like, there's just properties, very generally, broadly speaking, to a set of systems. And then you say it has a certain current, like, what potential? What, like that's just, it's a weird property to group there. So I agree with you in a real way. Like exchange current density is a weird metric that we
Yeah.
use because it's the current of this system, but current is dependent on potential. Like the current no, it's just the current.
Well,
You know,
yeah, I've thought it through too, like,
but to your point, that's why the heterogeneous rate constant makes more sense because that's a speed of the reaction occurring, and that makes more sense to use as a metric.
yeah, it makes more sense also because it's not dependent on area and
Right.
concentration, sort of say. Like
Yeah.
exchange current density is dependent on those two things,
Yeah.
which means it only really explains like one system.
Yeah.
It's only good for this one system under these specific conditions.
Yes.
So,
So I think that the I core and the E core are kind of along that line where it's like
yeah.
it's an intrinsic property of the
Mhm.
system,
Yeah.
but it's actually more related to things that probably would be better than a I and an E. Like it probably is
So,
more
so does
right. Like
so actually maybe this is a question then. If you are at the corrosion potential and that is defined by a quote corrosion current, um is it similar to like regular Tafel analysis that if I move slightly more positive of the corrosion potential, I'm now going to induce a lot of I'm going to observe a current associated with corrosion and oxidation. And if I move like negative of the corrosion potential, I'm going to start uh, I'll either see less of that current or no current or something along
in
those
theory,
lines.
yes. I mean, that is how you generate the data to calculate them is you actually do just that,
Yeah. Okay.
and because you don't know where E core is, we usually start near open circuit potential because it's usually close to that. It just, I mean, I think that there's probably a good reason for why those are very close together. Naturally, they're not exactly the same necessarily as we just described, but um, I mean, what you just described is like how you get the Tafel data to make a Tafel, the IE data basically to make those Tafel plots,
Hmm.
is you sweep positively for some indeterminate length of potential, usually 100 millivolts, 200 millivolts, something like that. And then you do the same in the negative direction. And then when you make your plots, that's when you determine, where the corrosion potential is. But you are doing just that, which is that if you, and again, the assumption being made here is that this is all kinetic current, which is accomplished,
Hmm.
roughly speaking, by sweeping very, very slowly and trying to minimize charging currents and, auxiliary processes and all that kind of stuff, or just making the assumption that it's mostly kinetic current, which isn't always true, but I digress.
Okay.
But effectively, right, is that you move far in one direction and you're effectively pushing it into an irreversible
Mhm.
direction in one or the other. So yeah, I mean, what you said is the case there, I guess.
All right, gotta look into this at some point. All right,
Yeah,
another thing for the list of things to learn.
like really, like I feel like that is one of those things that almost very few people probably like really understand,
Mhm.
and I am feeling that like I want to understand it at a deeper level, right?
Yeah, yeah.
Like
Well,
what is the E core and the I core? What exactly is it?
yeah. I mean, if it's the same as the, I mean, if it is literally the same as how we think about Tafel analysis, then it's like okay, then that
But
explains almost everything.
well, yeah, but it doesn't explain like what is it? What specifically is this potential? Why does it matter? What
Oh, what the
Well, if the
corrosion or why is it not the same as the open circuit?
yeah,
Well, okay,
because again, if it is the same as the open circuit potential, I core is always zero,
yeah, then I core is
and I
always
core
zero,
is not always zero.
and I core is not always zero. But I core is also an extrapolation.
Well, right, but it's so is E core.
E core is also an
And so
extrapolation.
if what we're saying, if E core was always the same as OCP, that plot I drew before, right? That intersection would always be at the middle where
It
those
will always
meet.
be at the
Because
middle.
on this plot, OCP is where those shoot to the left.
Yeah,
That's because it's infinity. That's where the x-axis goes to infinity or minus infinity, because the it's all the way to the left. it's log
Wait.
current,
Yeah.
right? This is
Wait, let's go-
just mathematically, like
Yeah.
this, the left of the axis here is, this is log, this is like minus infinity. So it's zero,
Right.
zero log of, it's
Yeah.
log of
well,
zero is infinity.
Yeah. Log
so
of zero is
it's either
infinity.
infinity that way or that way. So that's OCP. Like this is OCP.
Yeah. So that value is OCP.
And so these sometimes can intersect right there, but it doesn't always. That's the point.
Interesting.
And it also depends on where you take your slopes. Like there's a lot of subjectivity here, which is also what makes this even more complicated. But again,
Okay.
we're going to look at this later
Yeah.
and move on for now. But again, sorry for we're just talking through this, but it is one of those things that I do think not a lot of folks think about or know the answer to, us included.
Yeah.
And it's like,
Oh.
what is I-core and E-core? Like, what's a better definition for those? I'm going to add that to our list. We're going to try to figure that out.
Yeah.
Until then, Majibalan has asked, can you give a gist about overpotential? So that one we certainly can do. So overpotential, now forgetting everything we just talked about with E-core and I-core and all this kind of stuff, assuming you have a very simple reaction, okay? If I just have any electrochemical reaction, I'm not going to do the O in it. I'm just going to do A plus an electron gives me B. So I have any reaction. This thermodynamically will have some E0 of 100 millivolts. I'm just making up a number, right? So it has a standard thermodynamic potential. The overpotential is defined as the potential difference between the standard potential and where you're at. So if I apply 100 millivolts, my overpotential is 0. So let's say if I apply 300 millivolts, overpotential is equal to 300 minus E0, which is 100. So my overpotential is 200 millivolts. It means that I am applying 200 millivolts over the standard potential about which I'm studying. It goes negative as well, right? If I apply minus 200 millivolts, the overpotential is, that's an equal sign, minus 200 minus 100 is equal to minus 300 millivolts. So now I have a minus 300 millivolt overpotential, or you'd say 300 millivolts in the negative direction, or 300 millivolts reduction overpotential. These are all the same thing, but the direction matters. You can say that with a minus sign or a plus sign, right? Or you can just say it for oxidation or reduction. So those are all the options. But that overpotential is just a shifting of the potential axis about the standard potential of the reaction that you're studying. In this case, it's this A plus electron goes to B. So whatever you're studying, it has a standard potential. And so you're using that as your baseline instead of like 0 being your baseline. Now 100 is your baseline, whatever that potential is. So it's just moving the axis around based on whatever you're studying. You have anything to add?
Oh, yeah. I mean, all these things kind of come down to thermodynamics. So when you apply an overpotential, you're hoping to drive the reaction. This again also goes back to like the Nernst equation.
Always.
It always comes back to the Nernst equation. So let's actually bring that up, because this is a way you can think about it. So when you go back to the Nernst equation, and if I just get rid of all this ink that I have here, the main thing about overpotential, because Neil just said it. I mean, he just said you're literally looking at the difference, but like eta is equal to, you did E naught minus potential, or E minus
E minus E naught, I think.
E minus E naught. I just want to make sure I get that right.
Doesn't matter which direction you do, basically.
Yes. So, but it's just looking at these two numbers. And these two numbers affect the ratio of your oxidized and reduced species. So by changing the overpotential, or by applying a potential that's beyond the thermodynamic minimum, sort of say, you're driving either like this guy to go up or this guy to go down. You're affecting the equilibrium, the concentration, the relative concentration of these species at that particular potential. So that's another way that you can think about it. And because this is related to, say, the Gibbs free energy of the system, you're changing the thermodynamic driving force, if you will. So ideally, you don't want to, you want to have systems that have very low overpotentials, but sometimes if they are kinetically inhibited, then you have to drive a high overpotential to get a reaction to go forward. So and then that gets into Butler-Volmer, which we won't do now.
Nobody cares about Butler-Volmer. We only care about the Nernst equation.
That's true.
The Nernst equation is everything you need.
It is. Everything that you need. You don't need anything else. And Butler-Volmer eventually becomes the Nernst equation under certain conditions. Not the other way around, though.
No,
just letting you know that.
The Nernst.
Well, I'll let you
if
know.
If you're new to this program, folks, Alex loves the Nernst equation.
I love the Nernst equation. It's
I'm partial to the Butler-Volmer equation, but apparently it's derivative. So
I don't mind the Butler-Volmer equation. It's
I like
good.
it because it's one of my trigger points, which is that people make Tafel plots, not realizing that it comes directly from the Butler-Volmer equation.
Oh yeah,
and therefore it's kinetic information, and they just take a CV and they're like, "Look, it's a Tafel plot." And it's like, no, it's not. That's nonsense data, and your paper is nonsense paper. And your research is nonsense research. Sorry, yes, that was way more strong than I actually meant. I'm just kidding. But I'm not kidding. Stop making Tafel plots. Speaking of Tafel plots, how? Oh, sorry, this one's not about Tafel. No. Someone else asked about Tafel later. I thought that would be a good segue.
That's your other favorite subject.
I know.
All time.
Amazing. How charge transfer resistance in EIS evaluates catalytic activity in HER. So this is just basically Ohm's law here. The process, generally speaking, whether it's HER or anything else, when you are studying the charge transfer resistance, we look at a Nyquist plot most of the time. And so we have Z imaginary, we have Z real. And we have, if we're studying one process that looks like this, and then maybe you change the potential and it looks like this. Our charge transfer resistance, right, for the black one is the width of this semicircle here. And so this is RCT, let's just say 1. And then the width of this red one is smaller. So this is RCT2, right? Now, how does this relate to the catalytic activity? Well, we just honestly just look at Ohm's law, right? Ohm's law. And so we typically either write V is equal to IR, or we say E is equal to IR or IZ. So impedance, resistance, these are basically equivalent, but we'll just look at the resistance one here. So very simply speaking, if R is high, I is low, right? These are directly, inversely related to each other. So for any particular voltage, if your resistance is high, your current is low. And if your resistance is low, your current is high. Another way to say this is if you have a very low resistance, charge transfer resistance or otherwise, more current can flow. And if you have a very high resistance, it's preventing current from flowing. And so when we talk about electrocatalytic activity, how does the resistance relate to the catalytic activity or the electrocatalytic activity? Well, if something is preventing a lot of current from flowing, it's probably not doing very well catalytically, because the current flow is related to making hydrogen evolution reaction. You're making hydrogen. If not a lot of current is flowing, it's not making a lot of hydrogen, and so its catalytic activity is bad. So basically, we study HER or anything else with impedance by looking at the charge transfer resistance, and basically we are looking for something that has a low charge transfer resistance, which corresponds to higher current or less inhibited process, hence better activity. So that's kind of charge transfer resistance in a nutshell, whether it's for HER or anything else.
Yeah.
I would say. So
yeah, that's perfect.
Okay.
Let's see. We have another
Let's see,
question.
Leslie
is asking, "Hello, how are you? We're good.
We're doing very well.
Pretty good, thank you. I would like to ask how a potentiostat works to measure the corrosion rate of a metal.
LPR.
LPR. Oh, she just wants the technique.
I guess. I don't know if that's the question.
Yeah,
I guess.
or like, I mean, potentiostats work the same way no matter what the like what the chemistry is. The potentiostat's kind of doing the same thing. The applied potential and maybe the current ranges that you're looking at and the waveform will be different depending on what technique you're using.
Right.
But as Neil said, linear polarization resistance (LPR)
Here, I have this
is
tab
the
up.
technique.
Let me share
You have
this
the
tab.
Mhm.
I'll kind of. This is a page on our knowledge base of our website, for instance. Let me see if I zoom in, if it kind of shows a little better. So I'm not going to go through the whole page for you, but effectively, I just talked about Ohm's law. V is IR. So basically, how does a potentiostat work to measure the corrosion rate? Well, first of all, you get a measure of R, whether through impedance or something else, but the slope of a VI curve is R. This is all Ohm's law here. And so you're getting R. So this in corrosion, sometimes we call it RP, which is the polarization resistance. It just means that I've moved the potential, measured the current, and the slope of that is RP. And so how is the corrosion rate measured? Well, it's a bit of a somewhat complicated mathematical process, but you just follow the steps of these equations here. So we say that the R is equal to this constant B over I. B is defined this way. There's these Tafel constants, which goes back 20 minutes ago. We were talking about Tafel constants forever. Essentially, we relate the resistance that's measured by the potentiostat. To your point, how does the potentiostat measure? Well, the potentiostat doesn't measure the corrosion rate. It measures the current in the potential, which is used to calculate resistance, which is used to calculate corrosion rate. So there's like a multi-step process. So the potentiostat itself doesn't measure corrosion rate, but often it measures the I and the E, and then the software does calculations from those measurements to get corrosion rate. And so the corrosion rate, I came down here, I'm going to skip ahead, blah, 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 you do a lot of things. There's the corrosion rate. Sometimes it's expressed as a penetration rate, which is how much material is being destroyed over how much time. Sometimes it's calculated as a mass loss rate, how many grams are being lost per surface area, per day, per minute, per hour, per year, per millennium. Right. And so effectively, we are getting this again, E and I, we get a measure of the resistance. The resistance gives us a measure of the corrosion current, the I core as well. And so from some of those measurements, we are able to extract there's other constants here, like this is the density, and there's a proportionality constant anyway. Some of these things you can look into this afterwards if you'd like, but specifically, again, the potentiostat doesn't measure the corrosion rate. It measures E and I, and then a few calculations allow you to extract the corrosion rate, usually of metals like steel and things like that are what are typically measured. So and the last thing I'll say, of course, is that most I don't know if most, I suppose our company's software does all of those calculations automatically. For example, when you run a corrosion test and experiment, you set the parameters up appropriately, and then it outputs the corrosion rate for you automatically based on some of that mathematics that I just showed you. So
so let us know if you have any further questions or clarification on that. But moving forward, RS has a question. How can we define the region on Tafel plots to determine the right charge transfer coefficients? Charge transfer coefficients? Or is he talking about the constants? Or
I think you probably mean like the Tafel constants.
So
Tafel slopes.
Tafel slopes,
basically.
Maybe?
Yeah. I've talked about this a little bit before. I'll kind of try to recap. I tend to give, I'm trying to think how I like, I usually try to word this in a way. It's a hard answer, to be honest.
Mhm.
And a lot of the reason why it's a hard answer is because quite often your Tafel plot is not convenient and does not always make it obvious
Mhm.
where you should take the Tafel slope. So, like, for example, I'll just draw one half of the Tafel. I'm not going to draw both, like with the E-core kind of thing we talked about. But
Mhm.
like, if your Tafel plot is like that, well, it's pretty obvious. Here's my Tafel slope. It's like the flat region, right? Okay. Well, what if your Tafel plot is like a circle arc? It's like, do I take it here, 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 here? Like, where do I take it? Right. To your question, it's not easy. Now, um, I tend to try to give two suggestions, if you will, to this. All right. The first is, if you know, for instance, I'll skip over this for now for time or sort of running out. I want to make sure we get to every question.
Mhm.
Um, I'm assuming you know the 120 millivolts per decade is the number, so to speak, right? Um, for a Tafel slope of a one electron, um, transfer process, irreversible, the whole 9 yards. That's the slope. That's the Tafel slope, 120. So one of the ways of doing this is, where should I find my slope? Well, if I have a baseline tool on my plot and I do it here, it's let's see, this is 90. And then I take the slope here and it's, bless you. Bless you.
Thank you.
One
Sorry.
more and I'm going to
Mhm.
tax you. All right. But this is 180. Well, and I take it here and it's 120, right? I'm just making up numbers here, but like, okay, well then this is where I'm going to take my slope because, for instance, I know based on my knowledge of my system and theory of the kinetics of my process, that I should have 120 millivolts per decade. So even though it's a little bit murky, I can sort of, it's a weird way of saying this, but I would say like post hoc justify the voltage range. This is the voltage on the y-axis. So like, where should I pick? Okay, well, the voltage range where I find 120 millivolts. So it's like I'm choosing the slope to be what I want to justify what range of voltages I should apply it on. So it's like, it's almost backwards. I hope I understand that that's backwards, but um, it's a way to justify where am I taking my Tafel slope. It's like, well, I know that in theory it should be this slope, and so there's probably reasons why it's not behaving perfectly flat or whatever, but I can say, okay, well, this is roughly it. Now the other answer is to take, let's just say, the correct um, approach to this, which is that, okay, well, okay, I'm not going to make the slope be what I want it to be. I'm going to let it be whatever it ends up being. Okay. But one thing I can use to my advantage is that this 120 number serves two purposes. It is the ideal Tafel slope for a one electron irreversible process. It's also 120 millivolts is, roughly speaking, the amount of overpotential you need to be from the E0 for a process to be roughly irreversible. So if this is my E0 here, and my Tafel slope, my Tafel plot is, whatever, it's this. Then what I can say to myself is, well, I might want to take my slope here, but this is only, 50 millivolts away from E0. Well, I can say, no, I have to go at least 120 to, 200, whatever. The end point could be whatever, because I want to make sure I take an overpotential that's at least 120 millivolts from the E0, because that's where the slope, that's where it's actually irreversible, the process. And so I'm abiding by the assumption built into the Tafel equation, which is that at 120 millivolts away from the E0, I have about 99%, 1% of the oxidation or the reduction, which means it's roughly irreversible. So that's the other way to do this, is to say, well, I don't know exactly where to take the slope, but I'm going to at least start 120 millivolts away from the E0 and go to some number more, I don't exactly where should I go to 250? Should I go to 300? Like, it depends on how much data you have. So that part is a bit of a question mark, to be honest. But maybe you say, I want to start here. Again, for the reason that I'm making sure I'm satisfying the assumptions built into the Tafel equation. So those are the two strategies, I guess I would say, that I tend to suggest when it comes to determining where to take the Tafel plot, which voltage region, on the y-axis.
All right. Okay, moving forward. We have a question from Musi. He says, "Hello, hope you're doing well. How the radius of the semicircle is equal to the RCT? Could you please explain this?"
Sure. I can show my.
Yeah.
Let me pull up my webinar
Mhm.
slides. It's probably in this one. That one. Okay, I got it. Let me find the right slides. I'll try to show you where that comes from. Where is it? Where does it talk specifically about that? Go through the math. There we go. All right. I'm gonna. Sorry, I'm getting here. Show taskbar. All right. Let me share. I will go through a little bit of these slides from one of my webinars on impedance. I'll show you where that comes from. So I'm going to probably skip through some of this, I think. Let's see. So this is a Randall's or a Voigt element here, if you will. And this is where I talk through. Oh, this isn't sorry, this is the wrong one. This is the one that doesn't have animations.
Oh.
Only weirdos don't use animations. I use animations on everything. So, all right, sorry, let me get the right one. I want to, all right. There we go. Sorry for the delay. Here we are. Now, because without animations, it just doesn't work. You just don't even know what you're looking at. All right. Okay, so for this random Voigt element here, I'll just go through this briefly to kind of explain where the RCT comes from as the width of the semicircle. The first thing to review is Kirchhoff's laws. So when you have circuit elements in series, you add up the resistors or the impedances up to get the sort of total sum. And when they're in parallel, there's a 1/, sum. This is just a reminder of this mathematics. If you're not familiar with this, then this might be a little difficult for you, admittedly, but hopefully this is a reminder of how you add circuit elements and whether it's resistors or capacitors or everything, impedance as well. And so all I'm doing here is showing you for this, when you get a semicircle, you have this circuit element here, this RC in parallel. Capacitor is 1/j⍵c. So these are just the mathematics of the impedance of all the circuit elements involved. All right. When I do that solving, I sum the resistance, I sum up the impedance of the elements in parallel and the elements in series. And so the ones in parallel, it's this 1/, term here, and the ones in series, it's you add them up. And so all I can do is make this sort of simplified expression. All right. So this is the mathematics right here at the bottom, Z, for the impedance of omega as a function of frequency for this circuit, which makes the semicircle that you're thinking about. And so here's how this is a slide on the power of it in general, but what I'll do is I'll point out where you get the width of the semicircle. Okay. So we can look at two test cases. At high frequency, omega goes to infinity. What happens? This term right here, this goes away because 1/infinity is 0, right? So the impedance of the capacitor is basically 0 at high frequency. Okay. And so, let me get to the next slide. Sorry, I want to do it mathematically. Right. As I was saying, omega is in the denominator of this big term here at the bottom. So at infinity, RCT over 1 plus infinity, this whole term goes away. So at the highest frequencies, the impedance is equivalent to RS, just the ohmic resistance. So on the Nyquist plot here on the right, the high frequency point is the leftmost point. So that's why we say the x-intercept here at y is equal to 0. That's equivalent to the IR drop or the ohmic resistance RS, the series resistor, whatever term you want to use. Now, the other extreme is at 0 frequency or at low frequency as omega goes to 0. This term goes away, but I still have a 1. So it's RCT over 1. So at the lowest frequency, which is the rightmost point on my Nyquist plot, or the end of the semicircle, my impedance overall is RS plus RCT. And since RS is the leftmost point of the semicircle where it intercepts, well, then by definition, the difference is the width of this semicircle. So at the rightmost point, all the way over here, the lowest frequency, the impedance there, where y is equal to 0, the imaginary impedance is 0, is RS plus RCT. And so RS is the left, the width of the semicircle is RCT. So that's mathematically, that's where that comes from. I hope that's clear. I know I kind of went through that a little quickly, and some of the mathematics might be, if it's math isn't your favorite thing, then maybe that's a bit tricky to comprehend, I suppose. But that's where that comes from. That's mathematically how you show. And so whenever you have a resistor, capacitor, or CPE in parallel, the mathematics works out the same, that the width of that semicircle always ends up being equivalent to that resistor value. So the width of the semicircle, that's where it comes from.
Mhm. All right, very good. I think there's just one more question, which is good because it's about 2:50. We're fast approaching 2 hours. Chandan asks, why do people convert LSV to Tafel in HER? Why are they not calculating it directly from a potentiostat, which is, to say, the directly from the LSV data, sort of say? Well, first off, you have to just by the so assuming, and Neil will. I don't want to get Neil triggered, but yeah, assuming that you could just use regular LSV to get Tafel data.
It's a big assumption.
Which is it's a fairly decent assumption. You need to have current only associated with the kinetics of your reaction. So the rotating disc electrode is probably the best way to do that. Of course, you could also use, EIS. That might take a bit longer to do, but once you get purely kinetic current or current that's only associated with the faradaic reactions that are occurring, the Tafel analysis is really, the equations that govern it are fairly complex. That comes from the Butler-Volmer equation, and so there's naturally a natural log involved with it. And if you don't plot the natural log of the current versus the potential, so you must do some kind of transformations to it, you're not going to get Tafel slopes. And I know this is just kind of like a math thing, but we are trying. But people are usually trying to relate their catalysis information and data to heterogeneous rate constants and exchange current densities. And all of the math that's involved in those things comes back to Tafel and Butler-Volmer. So these things don't have like a square root dependence on like the scan rate, like in cyclic voltammetry. They don't have a rotation and square root of RDE dependence for the rotation rate. They have a logarithmic relationship, and so you need to plot. You need to create Tafel plots so that you have this logarithmic relationship, so that you can get a slope. Otherwise, unless you really like to fit logarithmic plots, just fitting whatever you are to a log instead of converting everything to a log and then doing a linear fit, like you could do that. It's just a change in the math, sort of say. But yeah, I hope that kind of I hope that answers your question. I don't know if you have anything to add.
No, I think that covers it. I don't have any.
Yeah.
It's really, it's just math. And I mean, I don't know. I guess it's like, why is a potentiostat not like potentiostats and software associated with the potentiostat just usually report the signals. And so sometimes there are those mathematical transformations built in, sometimes they're not, sometimes you do them yourself. But yeah, it's really just sort of a preference of mathematics. It's not something that, for instance, is like the potentiostat calculates it. The potentiostat calculates potential and current and time. That's it. That's all potentiostats do. Right? The software will do a lot of fancy stuff, but the potentiostat's job is to monitor E and I and time.
Yeah.
That's it. Every potentiostat, 100% of the time, that's all they're doing.
Yeah.
They make you think you're doing all sorts of fancy stuff. They're just measuring potential, current, and time. That's all electrochemistry is.
Yeah.
All of it. 100% of it.
Yeah.
There's nothing more. It's very, very boring. That's just the reality. So I think we'll get to Alex here. His question. It's a little bit. I could talk through this a little bit. Well, maybe this will be the last thing. Chris had asked what it looks like, and he said often it looks like sort of two parts of different semicircles, but very different, noisy, improper. Okay, so the question in general is, if I get incomplete semicircle, is such a Nyquist plot still modelable? So the answer is most of the time yes, though it depends how incomplete your semicircle is, and in general, the more resolved, I guess your features are, the better and probably more accurately and easily you'll be able to model them or circuit fit. But you don't have to have like complete features to be able to get measurements in general. However, the problem is, as you're describing it, you said you tried to increase the frequency range to resolve it. So one of two things is almost certainly true. Which is that you are working in a solid state system where you simply need capabilities of really high frequencies to be able to resolve some features, because there are very fast processes occurring in your solid state system. Or, which is I suspect is probably more likely the case, you are trying to resolve something that isn't real and doesn't matter. So what does happen sometimes, if this is a Nyquist plot, for example, Zi and Z real. Sometimes what happens when you get your Nyquist plot is you get this sort of feature like this, right? So here's your, this might be like your Randall's plot here. It looks nice, right? You have your charge transfer resistance and your diffusional tail. And you have this sort of curious high frequency thing. And so you say, oh, I'm at 100 kilohertz. And so let's go up to, 1 megahertz. And it's like, you get a little more data, or maybe it's even noisier. And it's like, okay, well, I'm trying to get this. This would lead me to believe there's another, Randall's element here, like there's another semicircle, another process. A lot of times that is not this is what we call artifact. It's an instrument artifact. It's a result of the reference electrode not being able to keep up its speed. It's a stray glass capacitance. It's basically instrument features that are not related to your chemistry. So in one way, my answer to you is, don't worry too much about trying to resolve or even fit this. You should probably cut these data off. And partly you can usually tell because it would work itself out that if you finished the semicircle, in many cases I've seen, it would finish at minus a minus, ZR, like it would finish in a negative territory. That doesn't really make any sense. There's no real meaning to that. So that right there is when that's the indication that is the case, that should tell you, oh, this is a feature I should just ignore. And I should consider, I can either try to use something like a shunt, which clarifies high frequency artifacts sometimes, or I can just ignore it and start here and just start from this point on. Oftentimes that's the best option. Especially when, again, it would resolve in negative territory. Now, the murky part comes if you don't have that situation and it is an unresolved peak same sort of idea, but it would, in theory, still finish at a positive ZR. Then you have a situation where this sometimes represents like an interface at the electrode sometimes, and the solid state kind of thing comes into play. Like, so if you have, for example, like a substrate in a film, and you have like your electrode, and you have like a very tight film on it, and then you have your electrolyte over here or whatever. Well, the interaction between the substrate and the film can manifest as this small semicircle at the really high frequencies. And that sometimes can be something that you do want to resolve, because you want to kind of just be able to measure, like, there's it's usually a small little high frequency semicircle, because it's like the resistance, there's not a lot of impedance. It's a pretty good, tight, sometimes it doesn't show up at all. Uh, you know, but it can be an indication of how well your film is on your material, for example. Sometimes that's the case. And so getting that resolved can be useful, right? Again, I don't have an answer, because sometimes it's hard to tell which of the two cases I just described, you have going on. Sometimes, either way, though, in a lot of cases, it's like your idea of resolving this kind of high frequency stuff is just for completeness. In my observation, most people are concerned with, this RCT, whatever the process they're studying. They want the Warburg information. It's like, you're not really interested in it. You're just trying to fit it for completion, which is understandable. You're trying to get an answer to what's happening. But in a lot of cases, it's like, you can probably just start. You can just, you might even just, for utility sake, ignore it, start at a lower frequency and ignore that feature if you're pretty sure it's not part of what you're really like measuring. So it might not even matter in all cases anyway. So that's just kind of my talking through that, I guess. Let me see. He says, thank you. I don't think it's due to setup, though. I'm testing different crystalline phases of the same compound. With one, I always get full semicircle. With another one, usually not. Yeah. So this might actually be some sort of a process. But like I said, too, in the beginning, is that in general, you can still fit like an RC, or RQ for an incomplete semicircle and get a result. Now, if it's like a tiny bit of the semicircle, it might not be, like, the accuracy will go down. But if you have like a quarter of a semicircle or half of a semicircle, yeah, of course you can fit it. You don't have to have the full thing resolved for one reason or another. Like, you can't go to high enough frequency, or you can't go to low enough frequency, or it doesn't behave super well at those extreme frequencies. But you can still extrapolate with a model, with a fit, and get a an estimate of the parameters involved, assuming it's not that artifact that I talked about.
Yeah. One thing I'm thinking about is, if you have like one redox molecule but different like crystalline faces on your working electrode, if it's affecting like the charge transfer resistance, for example, that's going to increase the width of your semicircle. So even if you're at like the same potential, you may find that, like, when you have something that's normal and it's a small semicircle and then your diffusional tail, like, it completes and it's no problem. But if the charge transfer resistance is super, super big, then by the time you get to the frequency normally where you're seeing Warburg stuff, you're still kind of charging that thing up. And actually, even Chris actually mentioned that, packing density and the electrical double layer might be playing some tricks, because the electrical double layer is changing based on the crystal face. That's another thing. But I think, to Neil's point, it's like, you don't need to have the entire thing to fit it.
Yeah.
If you're thinking about the entire chemical system.
Just be cautious, is the last part I would say, that it is modelable, like you say, Alex, and just be cautious that if you have a very small portion of a arc and you're extrapolating to a semicircle, that your accuracy will be obviously diminished if you only have a very small bit of the arc, because you can imagine you could fit that with like really big or really small, and it might still look like it kind of fits. So you might have to take some large, like, well, this is what I get for a estimate of the charge transfer resistance or the semicircle, but it's not terribly accurate because I don't have too much of the arc. But if you have like a a quarter or a third or half of the arc, then it probably is pretty accurate. So just keep some of that in mind, right?
Yeah.
And with that, I think we will call it a day.
Yes.
In a week.
Yes.
Again, a week early.
Yes.
A day early. Excuse me. I will not be with you next week, but I assume you.
Yeah,
will
I'll be around.
So
Should be around.
Alex will be able to answer
down the fort.
Yeah, and I will join the following week, most probably.
Yeah.
But until then, thank you very much, everybody. We appreciate it. We are rapidly approaching episode 100. I just wanted to mention that.
Yeah,
We're
yeah.
at like 87.
We're at like
88,
87 or
at this point.
something along those lines.
It just keeps going.
Which means I have to eventually make a bunch more
people keep
thumbnails.
People keep asking questions. Asking us questions.
Yes. Yeah.
Conjugating verbs is different. People ask us anything about electrochemistry.
Yeah, yeah. And this keeps us on our toes too.
Yeah. Like, well, now we're stuck trying to figure out what E-core and I-core are.
Yeah.
There's always something
to OCP.
There's always something. Now I need to think about it. So, well, we appreciate everybody keeping us honest and trying to be honest and help you with some of these difficult concepts. But in any case, much appreciated, and hope everybody has a great rest of their day and week and everything. And we'll see you next time.
Yeah. See you next time.